Welcome to this problem walkthrough. In this session, we'll explore LeetCode problem number 1530, titled Number of Good Leaf Nodes Pairs. This problem is a fascinating challenge that involves binary trees and pairwise computations. Let's dive in and explore the approaches to solving it. In this problem, we're working with a binary tree and an integer value called distance. The goal is to find pairs of leaf nodes in the tree that meet a specific condition. A pair of two different leaf nodes is considered good if the shortest path between the two nodes is less than or equal to the given distance. Your task is to return the total count of such good leaf node pairs. Now, let's recall that a leaf node is a node without any children. For the input, we're given the root of the binary tree and the integer distance, where distance is guaranteed to be between 1 and 10. The output will be a single integer representing the number of good leaf node pairs in the tree. To better understand the problem, let's look at an example. Here, we have a binary tree represented as root equals 1, 2, 3, null 4, and the distance value is 3. The tree structure is visualized as follows. Node 1 is the root, with nodes 2 and 3 as its children. Node 2 has a right child, node 4, while node 3 has no children. This tree contains two leaf nodes, 4 and 3. The output for this example is 1, which means there is exactly one good pair of leaf nodes. Focusing on this example further, the only possible pair of leaf nodes is 4, 3. To determine if this pair is good, we calculate the shortest path between these two nodes. The path starts at node 4, goes up to node 2, continues to node 1, and then moves down to node 3. This path has a total length of 3, which is equal to the given distance. Since the path length is within the allowed range, this pair is valid, and the output is 1. Now, let's examine another example to solidify our understanding. In this second example, the binary tree is represented as root equals 1, 2, 3, 4, 5, 6, 7, with a distance value of 3. The tree structure is fully balanced, with node 1 as the root. Nodes 2 and 3 are its children, and each of these has two children of their own, 4, 5, 6, and 7. This gives us 4 leaf nodes. Among these, the valid pairs of leaf nodes are 4, 5, and 6, 7. For both pairs, the shortest path has a length of 2, which is less than or equal to the given distance of 3. No other pairs meet the condition, so the output is 2. In the final example, the binary tree is represented as root equals 1 with a distance of 2. Here, the tree consists of just one node, which is the root itself. Since a leaf node is defined as a node with no children, this tree has no leaf nodes. Without any leaf nodes, there are no pairs to consider, so the output is 0. As we wrap up, note the problem's constraints. The tree can have up to 10,000 nodes, and the value of each node is unique. Edge cases to consider include trees with a single node, a distance of 1, or scenarios where all nodes are leaf nodes. Efficient traversal and distance computation will be key, especially for larger trees. To solve the problem of finding the number of good leaf node pairs in a binary tree, we started by exploring the brute force approach. The idea here is quite straightforward. First, we collect all the leaf nodes of the tree and then calculate the distance between every possible pair of these leaves. For each pair, we check if their distance is less than or equal to the given threshold distance. This involves traversing the tree to gather the leaf nodes, and for each pair of leaves, computing their distance using the lowest common ancestor, or LCA. Finally, we count the pairs that meet the condition. However, the brute force approach has significant performance limitations. Since computing the LCA for each pair is time-intensive, and there are many potential pairs to evaluate, the overall complexity becomes prohibitive, making this method impractical for larger trees. To address the inefficiencies of the brute force approach, we can use an optimized depth-first search, or DFS, combined with distance arrays. Here's how it works. Instead of comparing every possible pair of leaves, we maintain an array at each node where each element represents the count of leaf nodes at a specific depth from that node. By recursively computing these distance arrays for the left and right subtrees of each node, we can directly count valid leaf pairs by combining the arrays. Specifically, we check all pairs of leaf nodes from the left and right subtrees to see if their combined distance is less than or equal to the given threshold. After counting the valid pairs, we merge the distance arrays of the left and right subtrees to form the array for the current node. This approach avoids redundant calculations, and because the distance arrays are limited in size by the given parameter, it is both efficient and memory conscious. The optimized DFS approach offers significant improvements in both time and space complexity. For time, the algorithm runs in O, n*d, where n is the number of nodes and d is the given distance parameter, which is typically much smaller than the total number of nodes. Space usage is also efficient, requiring O, n plus d, to account for the recursion stack and the distance arrays. As an alternative, we could consider tree flattening, where the binary tree is converted into a graph representation. Using BFS or all-pairs shortest path algorithms, we could calculate distances between nodes. While this method is conceptually simpler, it introduces additional overheads, such as constructing the graph and storing an adjacency matrix. These factors make it less efficient than the optimized DFS, especially for larger trees, as its time and space complexity scale quadratically. Ultimately, the optimized DFS with distance arrays stands out as the most effective strategy for solving this problem. It offers a balance between simplicity and efficiency by utilizing recursion to compute distances in a structured way, avoiding the redundant pairwise comparisons seen in the brute force approach. This method is also more memory efficient than the graph-based alternative, as it only maintains distance arrays of limited size. While the implementation is slightly more complex than brute force, its time complexity of O, n*d, ensures it scales well with tree size, as long as the given distance parameter is reasonable. Notably, this approach directly counts valid pairs during the DFS traversal, streamlining the process and minimizing unnecessary computations. By combining clarity, efficiency, and scalability, the optimized DFS approach emerges as the ideal solution for tackling this problem. To solve this problem, we need to determine the number of good leaf node pairs in a binary tree. A pair of leaf nodes is considered good if the distance between them is less than or equal to the given distance. The key idea here is to use a recursive approach to traverse the tree. For each subtree rooted at a node, we will collect the distances of all leaf nodes from that root, count the number of good leaf node pairs by comparing the distances between left and right subtrees, and then pass the distances of these leaf nodes up to the parent node for further processing. The algorithm relies on a helper function we'll define as DFS node. This function will handle both the base case, where the node is null, and the recursive case, where we process the left and right children of the current node. The base case for our recursive function is straightforward. If the current node is null, we return an empty list since there are no leaf nodes. If the current node is a leaf, we return a list containing a single distance of 1, representing the distance of the leaf node to itself. For non-leaf nodes, we make recursive calls to the left and right children to obtain the distances of leaf nodes in their respective subtrees. Once we have these distances, we compare them to count good leaf node pairs. Specifically, for every distance d1 in the left subtree and d2 in the right subtree, we check if their sum is less than or equal to the given distance. If so, this is a good pair, and we increment a global counter that tracks the total number of good pairs. After counting, we increment each distance by 1 to account for the current node and return these updated distances to the parent node, ensuring the propagation of data up the tree. To optimize the algorithm, we introduce some important implementation details. We use a global counter to maintain the total count of good leaf node pairs, avoiding the need to pass intermediate results between function calls. At each node, we only track distances up to the given distance. This prevents us from storing unnecessary data and reduces computational overhead. The algorithm leverages a divide and conquer strategy, where each subtree computes partial results that are combined as we move back up the tree. By pruning distances greater than the given distance, we optimize memory usage and eliminate redundant calculations. These design choices ensure that the algorithm is both time and space efficient, as it avoids comparing every possible pair of leaf nodes across the entire tree. To implement this algorithm, we rely on specific data structures for efficiency. First, each node maintains a list of distances to its leaf nodes. This allows us to perform pairwise comparisons of leaf nodes between subtrees without duplicating work. Second, we use a global counter to track the total number of good leaf node pairs, which minimizes additional memory usage. In terms of complexity, the time complexity is approximately O, n** distance. This is because we visit each node exactly once and compare distances from the left and right subtrees, limiting the comparisons to the maximum allowed distance. The space complexity includes the recursion stack, which requires O, H, space, or H is the height of the tree, as well as the space for storing distances, which depends on the number of leaf nodes and the distance parameter. To further refine our understanding, we consider some edge cases. If the tree is empty, meaning the root is null, the result is 0 since there are no leaf nodes. For a single node tree, there are no pairs of leaf nodes, so the result is also 0. For very large trees, the algorithm remains efficient because it avoids storing unnecessary distances and limits comparisons to relevant subtrees. On the other hand, if the distance parameter is very small, such as 1, the algorithm skips most comparisons since very few leaf nodes can satisfy such a strict condition. These considerations ensure the algorithm is robust and performs well under a variety of scenarios. Finally, the pseudocode outlines the implementation, starting with a global counter initialized to 0 and a recursive function DFS that processes each node to compute distances and count good pairs. The pseudocode begins with a base case where, if the node is null, we return an empty list. For leaf nodes, we return a list containing a single distance of 1. Next, we make recursive calls to process the left and right children of the current node, collecting their respective distances. To count good leaf node pairs, we iterate over all combinations of distances from the left and right subtrees and check if their sum is less than or equal to the given distance. If so, we increment the global counter. After counting, we increment each distance by 1 to account for the current node and return the updated distances, ensuring they remain within the allowed range. Finally, we call the DFS function on the root node to compute the result and return the global counter. This implementation is efficient, concise, and incorporates all the optimizations discussed earlier. This solution uses a depth-first search (DFS) approach to traverse the binary tree and compute the number of good leaf node pairs. The DFS function is a helper function that recursively processes each node and calculates the distances of leaf nodes in its subtrees. 1. Base cases. If the node is none, it returns an empty list because there are no distances to compute. If the node is a leaf, it returns a list containing only 1, representing the depth of the leaf. 2. Recursive calls. The function calls itself recursively for the left and right subtrees to compute the distances of leaf nodes from the current node. 3. Pair checking. It iterates over all pairs of distances from the left and right subtrees and checks if their sum is less than or equal to the given distance. If the condition is satisfied, it increments the result counter. 4. Return statement. The function returns a list of updated distances by incrementing each distance by 1, to account for moving one level up in the tree. It filters out distances that exceed the given distance since they are no longer relevant for further computations. Finally, the countPairs method calls the DFS function on the root node and returns the total count of good leaf node pairs. This approach efficiently computes the result in O(n) time, where n is the number of nodes in the binary tree. Here, we begin our Java implementation by defining a solution class that contains the core logic to count the number of good leaf node pairs. We declare a private integer variable named result to keep track of the count. The main method, countPairs, accepts the root of the binary tree and the maximum allowable distance between leaf nodes. Inside this method, we call a helper function, DFS, which performs a depth-first search on the tree, and finally, we return the result. Now, the DFS method is where most of the logic resides. First, we handle the base case. If the current node is null, we return an empty list as there are no distances to calculate. If the node is a leaf, meaning it has no left or right children, we create a list containing just the depth of the leaf, which is 1, and return it. This allows us to propagate the depth information upwards in the tree. For non-leaf nodes, we recursively calculate the distances from the left and right subtrees by calling DFS on the left and right children. This sets the stage for evaluating the distances between leaf nodes in the left and right subtrees. Now, we evaluate all possible pairs of distances between the left and right subtrees. For every combination of distances from the left and right lists, we check if the sum is less than or equal to the specified maximum distance. If it is, we increment the result counter because we've found a valid pair of leaf nodes. Once we calculate the result for the current node, we prepare to return updated distances to the parent node. To do this, we create a new list to store distances from both subtrees, incrementing each distance by 1 to account for the current node's depth. However, we ensure that only distances less than the maximum allowable distance are added to the list, as larger distances are irrelevant for further calculations. This pruning step helps optimize the algorithm by reducing unnecessary computations. After combining the updated distances from both subtrees, we return this list to the parent node for further processing in the recursive calls. Finally, we define the structure of the tree nodes with the treenode class. Each node has a value and pointers to its left and right child nodes. We include a default constructor, a constructor that initializes the node with a value, and another constructor that initializes the node with a value and its left and right children. This structure is essential for representing the binary tree and passing it to the countPairs method. With these components in place, the implementation is complete and ready to efficiently count the number of good leaf node pairs in a binary tree. Here, we start with a simple binary tree consisting of 3 nodes, 1, 2, and 3. The goal is to find good leaf node pairs within a distance of 3. To solve this, we use a depth-first search, or DFS, approach. Starting at the root, node 1, we see that it is not a leaf, so we proceed to explore its left and right subtrees. First, we perform DFS on the left child, node 2. Node 2 is a leaf because it has no children. As a result, it returns a list containing the depth, 1, to its parent, which is node 1. These depths are stored in the left_distances array for node 1. This completes the exploration of the left subtree. Next, we perform DFS on the right subtree of node 1, starting with node 3. Similar to node 2, node 3 is also a leaf, so it returns 1, representing its depth. This depth is stored in the right_distances array for node 1. Now, at node 1, we check for good leaf node pairs. We compare all combinations of distances from left_distances and right_distances. For the pair L equals 1 from the left and R equals 1 from the right, the sum is L plus R equals 2, which is less than or equal to the given distance of 3. This qualifies as a good pair, so we increment our result count by 1. Finally, before returning, we increment all distances in both left_distances and right_distances by 1 to account for the additional depth when passing the values up the tree. Node 1 returns 2, 2 to its parent, though in this case, it has none. The final output for this tree is one good leaf node pair. Now, we examine a larger tree with 6 nodes. The allowable distance remains 3. Starting DFS at the root, node 1, we see that it is not a leaf, so we explore both its left and right subtrees. For the left subtree, we move to node 2, which is also not a leaf. From here, DFS proceeds to node 4. Node 4 is a leaf, so it returns 1 to its parent, node 2. Since node 2 has no right child, right_distances is an empty array. At node 2, we increment the distances from the left child by 1 and return 2 to its parent, node 1. Next, we begin exploring the right subtree of node 1, starting with node 3. Node 3 is not a leaf, so DFS continues to its children, nodes 5 and 6. Starting with node 5, we find that it is a leaf, so it returns 1. Similarly, node 6 is also a leaf, so it also returns 1. At node 3, we now have left_distances equals 1 and right_distances equals 1. We check all pairs of distances between the left and right children. For the pair L equals 1 and R equals 1, the sum is L plus R equals 2, which is less than or equal to the distance of 3. This forms a good pair, so we increment the result count by 1. Before returning to the parent, node 3 increments these distances by 1 and returns 2, 2 to node 1. Finally, at node 1, we compare left_distances equals 2 from node 2 and right_distances equals 2, 2 from node 3. However, no pairs satisfy the condition L plus or less than or equal to 3. The final output for this tree is one good leaf node pair. In this edge case, we have a tree with only a single node, which is the root, node 1. Since there are no other nodes, node 1 is considered a leaf. During DFS, it directly returns 1 as its depth. However, because there is only one node, there are no pairs of leaf nodes to evaluate. As a result, the final output is 0 good leaf node pairs for this tree. To analyze the time complexity of our solution, we start with the depth-first traversal performed by the DFS function. This traversal visits each node exactly once, which means it contributes O, n, to the overall time complexity, where n represents the number of nodes in the tree. Additionally, for each internal node in the tree, the algorithm evaluates all possible pairs of distances between leaf nodes in its left and right subtrees. If we let L and R denote the number of leaf nodes in the left and right subtrees respectively, the number of pairs to evaluate is O, L asterisk R. Summing this across all nodes in the tree, the total complexity for pair checking becomes O, L squared, where L is the total number of leaf nodes in the tree. Lastly, the algorithm also filters and increments distances after computing valid pairs. This step involves iterating through the combined list of distances, which is at most O, L, for each node. However, this step is relatively negligible compared to the pair checking process. Combining these factors, the overall time complexity in the worst case is O, n plus L squared. For balanced binary trees, the total number of leaf nodes L can be at most O, n/2, which means the pair checking term dominates, resulting in a worst case complexity of O, L squared, or equivalently O, n squared. On the other hand, in the best case scenario, such as in a highly unbalanced tree, the pair checking term becomes negligible, and the time complexity simplifies to O, n. Now turning to space complexity, we analyze the recursive call stack used during the depth-first traversal. The depth of this stack is equal to the height of the binary tree. In the worst case, where the tree is completely unbalanced, the height could be O, n. For a balanced tree, the height is reduced to O, log n, making this a significant factor in the overall space complexity. Additionally, the algorithm maintains lists of distances for leaf nodes at each level of recursion. The combined size of these lists is proportional to the total number of leaf nodes, contributing O, L, to the space complexity. Therefore, the overall space complexity in the worst case is O, n plus L, where O, n, accounts for the call stack and O, L, accounts for the leaf distance lists. For a balanced tree, this simplifies to O, log n plus L. Comparing this optimized approach to a naive method provides further insights. A brute force solution would involve enumerating all pairs of leaf nodes in the tree and calculating their distances. Since computing the distance for each pair requires traversing the paths, the time complexity for this approach balloons to O, L squared asterisk h, where h is the height of the tree. In contrast, the optimized solution drastically reduces redundant computations by using depth-first traversal and localized pair checking, achieving a more efficient complexity of O, n plus L squared, in the worst case. To summarize the best, average, and worst case scenarios for the optimized solution, we start with the best case, which occurs in a highly unbalanced tree where all nodes form a single branch. Here, pair checking is negligible, resulting in a time complexity of O, n. In the average case, such as in a balanced tree, the pair checking step dominates, leading to a complexity of O, n plus L squared. Finally, in the worst case, where the tree contains many leaf pairs and a large number of these pairs fall within the valid distance range, the complexity approaches O, n squared. Overall, the optimized solution significantly outperforms the naive approach, especially in cases where the number of leaf nodes is relatively small compared to the total number of nodes. This efficiency makes it a practical choice for solving the problem across a wide range of tree structures. When solving this problem, there are a few common mistakes to watch out for. First, not accounting for edge cases like very small or unbalanced trees can lead to incorrect results. For example, a tree with fewer than 2 leaves or a highly skewed structure often exposes flaws in the logic. Testing with edge cases such as a single-node tree or a tree where all nodes are on one side is essential. Another frequent issue is with distance calculation. It's important to remember that the distance between two nodes is not just the number of edges in their subtree but must also consider paths that pass through their parent or the root. Using depth-first search is a reliable way to ensure accuracy here. Additionally, many naive implementations rely on pairwise checks for all leaf nodes, but this results in O, n squared, time complexity, which is inefficient for larger trees. Instead, leveraging post-order traversal can significantly optimize this process. Lastly, don't overlook space constraints. Storing all leaf nodes or excessive intermediate data can consume a lot of memory. Recursive techniques can often help minimize space usage, so aim to design your solution with this in mind. Now, another common pitfall is hard-coding depth or distance limits. This often makes solutions less flexible and prone to errors, especially if the constraints change. Instead, dynamically derive these values based on the input. In interviews, it's worth noting that post-order traversal is a powerful tool for tree problems, particularly when information from subtrees is required. Practicing this pattern will help you approach similar challenges with confidence. It's also important to be ready to explain your choice between recursion and iteration. While recursion is more natural for tree problems, it can lead to stack overflow in very deep trees if not handled carefully. Highlighting the trade-offs between brute force and optimized solutions is another key point. Clearly discussing time and space complexities and justifying your improvements will show a strong understanding. Finally, don't forget to emphasize how you handle edge cases in testing. Interviewers value candidates who proactively account for all possible scenarios, as it demonstrates thoroughness and attention to detail. Now let's explore some related problems and alternative approaches. Problems like LeetCode 543, diameter of binary tree, involve calculating distances between nodes, which is directly relevant here. Similarly, LeetCode 124, binary tree maximum path sum, focuses on paths, sharing similarities with leaf pair calculations. LeetCode 863, all nodes distance k in binary tree, also deals with distance-based computations, and LeetCode 236, lowest common ancestor of a binary tree, highlights the importance of efficient traversal and understanding node relationships. When it comes to solving the problem, the brute force approach has the advantage of being straightforward and easy to implement. However, its inefficiency, due to the O(n)² complexity, makes it unsuitable for larger inputs. A more optimized approach is using DFS with backtracking, which reduces time complexity to O(n) by aggregating distances during a post-order traversal. While more efficient, this method is slightly more challenging to implement and debug. Alternatively, level-order traversal with distance tracking can be a good choice, especially for balanced trees. This iterative approach avoids recursion but can increase space complexity due to the queue required for level-order processing. Each of these methods has its pros and cons, so choose the one that best fits the problem constraints and your familiarity with the techniques. Thank you for joining me on this problem-solving journey. To recap, we tackled the problem of finding good leaf node pairs in a binary tree using depth-first search and optimization techniques. I hope this session gave you new insights into tree traversal and pairwise computation strategies. If you enjoyed this, please like, share, and subscribe for more coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!